Good evening, ladies and jelly babies, and welcome to my quantum computer wrote a podcast. My name is Dr. Dr Alexis Kirke, and I'm an alcoholic, but of course I'm not. In this episode, we'll be looking at something that I've always wanted to do, which is to include some quantum mathematics over some quantum-generated music. And one of my favourite yet very simple pieces of quantum mathematics is the teleportation algorithm. So I will now recite over the top of this track the teleportation algorithm demonstration and proof in the Dirac notation. And I will also explain that about a third to a half of all the tunes that you hear generated in this piece of music are generated by the IBM Q14 Melbourne and the algorithms that I've been running on it. To demonstrate the teleportation algorithm, suppose Alice has a qubit. QA equals A ket 0 plus B ket 1. And that Alice and Bob share an entangled pair. EP equals ket Q0 Q1 equals ket 0 0 plus ket 1 1, where Alice has Q0 and Bob has Q1. Because they are entangled, Alice's complete state is defined as A equals brackets A ket 0 plus B ket 1 close brackets ket 0 0 plus ket 1 1 close brackets. Equals A ket 0 ket 0 0 plus B ket 1 ket 0 0 plus A ket 0 ket 1 1 plus B ket 1 ket 1 1 equals A ket 0 0 0 plus B ket 1 0 0 plus A ket 0 0 1 plus B ket 1 1 1. This is a joint state. It does not mean that the qubit to be transmitted has been entangled with anything. However, now Alice does perform this extra entanglement. She entangles the qubit to be transmitted with the already entangled pair EP. This is done using a CCX C0 gate. Alice performs two operations. Firstly, a C0 of QA upon her part of the entangled pair, and secondly, an H gate on the qubit QA to be teleported. For clarity, we will write the entangled pair EP in as this. EP equals ket 0 0 plus ket 1 1 equals ket 0 plus ket 1 equals ket 0A ket 0B plus ket 1A ket 1B. with A and B representing Alice and Bob, although the following calculations are done based on Alice's actions. The whole state vector is written out in full, including Bob's part of the entangled pair. Then the C0 of QA upon Alice's part of the entangled pair is calculated as follows. Recalling that CCX is a linear operator. CCX open brackets QA, comma, cat 0A, cat 0B plus cat 0, cat 1A, cat 1B, close brackets equals CCX brackets A, cat 0 plus B, cat 1, comma, cat 0A, cat 0B plus cat 1A, cat 1B, close brackets, equals CCX A cat 0, comma, cat 0A, cat 0B plus cat 1A, cat 1B, brackets, plus CCX brackets cat B1, comma, B, 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 CCX brackets B cat 1, comma, cat 0A, cat 0B plus cat 1A, cat 1B, close brackets, equals
CCX brackets A0, A cat 0, comma, cat 0A, cat 0B, brackets plus CCX brackets A cat 0, comma, cat 1A, cat 1B, brackets plus CCX brackets B cat 1, comma, cat 0A, cat 0B, brackets plus CCX brackets B cat 1, comma, cat 1A, cat 1B, brackets.
the CCX is being done by Alice, so only affects the qubit state of her part of the entangled pair, equals A cat 0, cat 0A, cat 0B plus A cat 0, cat 1A, cat 1B plus B cat 1,
cat 1A, cat 0B plus B cat 1, cat 0A, cat 1B. As stated, the second operation which completes the teleportation is to for Alice to perform an H gate on the qubit QA. To be teleported once again, note that it will only affect that qubit and that H is a linear operator.
Also, the scalar weightings generated by H will be left out here, as they do not affect the calculation for the purposes of this explanation.
Equals H brackets A cat 0, close brackets, cat 0A, cat 0B plus H brackets A cat 0 brackets cat 1A, cat 1B plus H brackets B cat 1 brackets cat 1A, cat 0B plus H brackets B cat 1 brackets cat 0A, cat 1B, equals A H brackets cat 0, cat 0 A, cat 0 B plus A, H brackets cat 0 brackets cat 1 A, cat 1 B plus B, H brackets cat 1 brackets cat 1 A, cat 0 B plus B, H brackets cat 1 brackets cat 0 A, cat 1 B. Equals A brackets cat 0 plus cat 1 brackets cat 0 A, cat 0 B plus A brackets cat 0 plus cat 1 brackets cat 1 A, cat 1 B plus B brackets cat 0 minus cat 1 brackets cat 1 A, cat 0 B plus B brackets cat 0 minus cat 1 brackets cat 0 A, cat 1 B. Equals A cat 0, cat 0 A, cat 0 B plus A, cat 1, cat 0 A, cat 0 B plus A, cat 0, cat 1 A, cat 1 B plus A, cat 1, cat 1 A, cat 1 B plus B, cat 0, cat 1 A, cat 0 B minus B, cat 1. Cat 1 A, cat 0 B plus B, cat 0, cat 0 A, cat 1 B minus B, cat 1, cat 0 A, cat 1 B. Now, the terms involving what Alice can observe, the qubit QA, cat 0 A and cat 1 A, are factored out. Clearly be seen what is Alice's part of the total state, and what is Bob's part. Bob's part is said louder. Equals 0 cat A.
Bracket A, cat 0 B plus B, cat 1 B plus cat 1, cat 0 A, brackets A, cat 0 B, minus B, cat 1 B, plus 0, cat 1, cat A, brackets A, cat 1 B, plus B, cat 0 B, brackets, plus cat 1 A, brackets A, cat 1 B, minus B, cat 0 B. So, if Alice makes an observation of her qubit to be teleported and her part of the entangled pair, the joint state will collapse to one of the four terms in the state above by the axioms of quantum mechanics. Bob's state is affected by the collapse due to the entanglement. So, the new joint state across Alice and Bob will be one of cat 0 A, brackets A, cat 0 B plus B, cat 1 B, cat 0 cat 1 A, brackets A, cat 1 B plus B, cat 0 B, cat 1 cat 0 A, cat 0 B minus B, cat 1 B. Cat 1 A, cat 1 B minus B, cat 0 B. This completes the quantum part of the teleport send. Because Alice has actually observed her state, she knows whether her two qubits are 00 01, 10 or 11. Thus, she also knows which of the 4 Bob states Bob now holds. So, if Alice sends 2 classical bits, she can tell Bob which state he has. 00 for the state first, 01 for the second loud state, 10 for the third loud state, 11 for the fourth loud state.
If Bob receives 00 as the classical bit pair, he knows he's already got Alice's qubit. If he receives 0110 or 11, there are a set of simple quantum gates he can apply to his qubit state to convert it to Alice's. For 01 it is a Pauli X gate. For 10 it's a Pauli Z gate. For 11 it is a Pauli Z gate followed by a Pauli X gate. So Bob now holds Alice's qubit. Alice's qubit has been destroyed at Alice's end because she observed it.
Now follows a brief outro to explain which parts of the tune were by the quantum computer hardware device. There were 2 key tunes that were used from the IBM Melbourne Q14. The first one was a short tune, which was used in 3 ways. Here are the 3 ways that the tune was used. The second was a longer tune that was used in 3 ways in the music. There are 2 elements to note in these tunes. First of all, you will notice that in the second tune, it seemed to be made up of notes that were short followed by long and short followed by long in most cases. The reason for this is that part of the composition algorithm on the quantum computer was a Grover circuit, and this Grover circuit allowed the system to control the rhythmic nature of what was being produced. And one of the things the Grover system did, the solution created short notes followed by long notes. The other thing to note is the way that the tunes tend to move upwards. Now, the original quantum algorithm that I produced doesn't have this tendency when it's run in simulation. But when it's placed on an IBM Q14 Melbourne, the IBM quantum computer does have some imperfections, as do all quantum computers. It has certain errors. And these errors have the effect of making tunes tend to move upwards in pitch. I will now say a little bit, in case you're interested, which many of you won't be, about the actual system that was used. This system is from a paper that I am just completing now. It should be available on arXiv fairly soon. It's called Implementing a Hybrid Quantum Multi-Agent System Architecture in Hardware to Utilize the Quantum Speed Advantage in Real-Time Computer Music. A snappy title, I know. The actual system is a multi-agent system, and the 2 tunes that you can hear, they are from agent number 4, which is a quantum agent. The system has 2 quantum agents, 2 classical agents, and 1 sort of bridging agent that allows the quantum and classical agents to communicate, to produce music. The classical agents were myself playing on a keyboard and a sort of traditional computer music algorithm. The quantum agents both contained 2 Grover circuits, and these circuits allowed the quantum agents to sort of put their signature upon what was happening in the music. The bridge agent takes the 2 tunes from myself and from the traditional computer music AI, and it puts them into superposition. The actual weighting used to produce the 2 tunes in the EDM track you've just heard was 80% for the human and 20% for the classical computer algorithm. This superposition is then sent to agents 4 and 5 using teleportation, because that's the only way you can really communicate quantum information. The agents 4 and 5, the quantum agents, then replace some of the musical information with the results of some Grover solved musical rules that they contain. And these rules are essentially their musical character. And as I already said, those 2 tunes that were used again and again in the dance track you've just heard were outputs from Agent 4. In fact, they were 2 observations of the same state. But because the superpositions and the Grover results are non-deterministic, we got significantly different tunes from them, which is one of the nice things about quantum computer music, because you often like in music to not have things deterministic. But I would like to highlight that's not enough of a reason to use quantum computers to make music. The real innovation, if you like, in this paper that I'm writing is that it utilises the Grover algorithm, which has been proven to be faster than classical versions of the algorithm, much faster in fact, and also the use of teleportation to allow a quantum multi-agent system to work. And in fact, as far as I'm aware, it is the first quantum multi-agent system implemented on a hardware quantum computer, and certainly for the purposes of computer music. And that, as they say, is the end of that.